Lecture number 7, Soil Field Tests and Reports. So there are different boring techniques that are used for soil testing: open hole, auger boring, wash boring, and casing, and three main field tests: a standard penetration test, SPT, cone penetration test, CPT, and dynamic cone penetration test, DCP. So the important things that we can learn or identify from a core sample includes type of rock in the area, texture of soil, degree of stratification or lamination, orientation of rock formation, and presence of weathering, fracture, and faults. With respect to planning for core boring, the number of boring that is required for a project can be different. Typically, for larger structures, the spacing between the borings is between 50 feet to 100 feet. For a smaller one-story building, earth dam, it's usually spacing is between 100 feet to 200 feet. And then for highway projects, it can goes up to 500 to 1,000 feet. With respect to the depth, uh, the boring continues until acceptable bearing capacity is obtained. Um, for again larger structures with a heavier load, where we need to extend or continue the boring until we reach the bedrock. Okay, so the field test. The first field test that we will look at is a standard penetration test, or SPT. You can see the test setup here in this picture. The SPT test, this is one of the most commonly performed field tests that is used to evaluate bearing capacity of soil. It has a split spoon sampler. So at the here we have the split spoon sampler. Then it also has a hammer, 140 pound, and the hammer is dropped on the rod and split spoon sampler from a distance of 30 inches. The measurements done by SPT is how many drops is required for the split spoon sampler to penetrate the last 12-inch. And that number is referred to as N value, or standard penetration resistance value. So as you can see in this slide, we have a hammer. The hammer is dropped on the rod and a split spoon sampler from a distance of 30 inches. And this is the split spoon sampler. It's pushed into the soil in 3 increments: first increment, second increment, and third one. Each one is 6 inches. The first one is sitting, and then we have 2 more 6-inch increments. An N value, or SPT resistance value, is the number of drops or number of blows required for the last 12-inch penetration. So this is the SPT equipment. We have a rod. A split spoon sampler is connected to the rod, and a hammer is used to push the rod and split spoon sampler into the soil. As you can see, the sampler, you can open it and then you have a soil sample inside the sampler. That's why it's called a split spoon sampler. And a main characteristic of SPT test, a standard penetration test, is that it provides a soil sample for further laboratory testing. So, by performing the test, we can find N value or SPT resistance value, but also using the split spoon sampler that you see in this video, it also provides us with a soil sample for further laboratory tests. SPT, as I said, is the most widely field test performed for soil evaluation. It's simple, inexpensive, and it provides a soil sample. This table provides the correlation between SPT N value and relative density of sand. So this is just for sand. There is a correlation between relative density of sand and SPT N value. As you can expect, a lower SPT, easier penetration into the soil, loose material. Higher SPT N value is harder for the rod to penetrate into the soil, which means that we have a denser material. So we have an SPT value, we can relatively, we have a relative density, and we can describe our sandy soil. This table shows the relation between SPT N value and consistency of clay. QU is unconfined compressive strength of clay. Again, a lower SPTN value represents a softer clay, a softer soil, and a lower compressive strength. With an increase in SPT resistance, we will have a harder soil, and also we can expect a higher unconfined compressive strength. The next field test is called cone penetration test. This test is very similar to SPT, a standard penetration test, but instead of using a split spoon sampler, a rod with a cone on the tip is used. This test is very popular in Europe. It's gaining more attention in the US. It's rapid. It again pushes a rod that has a cone on the tip into the soil and measures the resistance. So this is how it works. It's a continuous hydraulic push, and there is an extension, so they push the rod that has a cone on the tip into the soil and then add the extension. Another characteristic of CPT is that it's a continuous test. For SPT, you need to make the boring. When you reach the layer, then you attach the split spoon sampler and do the SPT. So it will disturb our soil in the area. But CPT is a continuous test. There is no disturbance to the different layers of soil. and it measures cone resistance and frictional resistance of soil. So it's again a simple test. It's a fast test. It's continuous. It doesn't cause disturbance to the soil. A rod is pushed into the soil, and at the same time, the resistance, the frictional resistance, and tip resistance are measured. So SPT is a simple test, widely used. It provides us with a soil sample suitable in many soils. It causes disturbance. It's not continuous. And there, because of disturbance, there is high variability in the results. It's not suitable for very soft or very loose soil. CPT is also fast, continuous. Uh, you can do the quality control. It's suitable for different types of soil. Cons, it doesn't provide us with a soil sample. It's not done as many times as SPT is performed, so it has a smaller database, and it's unsuitable for very hard or dense soils and large particles. We also have a test that is called Dynamic Cone Penetration Test, DCPT. It basically combines different features from CPT and SPT together. So there is a dropping hammer fallen from 20 inches, but it measures the penetration depth per blow for each tested depth. Uh, but it has the shape of CPT, so it's a rod that has a cone at the tip. It's a good choice for shallow testing applications such as roadbed construction and maintenance. It's hand powered, so it's portable, it's easy to move, but it doesn't provide the same accuracy as SPT or CPT. Okay, so this is DCPT, Dynamic Cone Penetration Test. We also have an equipment, very like simple equipment that is used to measure shear strength of clay. That's another property of soil that is used in foundation design. And this basically, the equipment is a four-bladed vane shear device, and it's connected to a rod. You push the rod and the device into the soil, and then apply a torque, measure the resistance, and then using the torque required to shear the soil, diameter of vein tester, height of vein tester, you can find shear strength or cohesion of clay. So this is what we are trying to find, C or cohesion of clay. And there is a simple formula, simple equipment. You can use this equipment to find shear strength of clay. And also we talked about unconfined compressive strength. So this is also a simple test that can be done on a soil sample. So you see there is a cylindrical soil sample. This is unconfined, so you can see your soil sample. There is nothing holding the sample together. It's unconfined compressive strength. Compressive load is applied to the soil sample until failure of the sample. We record the load that is applied and the deformation caused by that load, and then we can make the stress strain curve for our soil sample and also find the unconfined compressive strength, which is basically the maximum strength. Soil report interpretation. So what is a soil report? It's a document that contains information about the subsurface structure and composition. The most important reason for examining the subsurface is to ensure the structure's foundation will be sufficiently supported. This means the subsurface must have sufficient bearing capacity and will not be subjected to unacceptable settling characteristics. So there are different reasons to perform subsurface soil, dewatering quantity, and cost of excavation. We need to make sure that nearby structures are not adversely affected by excavation. It really depends on how big the project is. Some reports can be elaborate with thousands of dollars spent to examine the subsurface structure and provide recommendations on how this examination will affect the project being proposed. So in a soil report, you will see the scope and purpose of the project, geologic setting, field testing, including the conditions, raw data and findings, laboratory testing, analysis, conclusion, and recommendation. For your project, for your lab report, you also need to provide a similar document. Your document doesn't have the field tests section, but it still has like an introduction. Where did you get the sample from? Geologic setting, laboratory testing, how to do the test, the data that you collected, analysis of the data, and then at the end provide a summary of your findings. So there are examples available on your As You Learn page, geotechnical lab reports. As I mentioned earlier, a soil report has a project description. Construction will include a 4-story above grade educational building with more useful information about the project. Purpose of a study. The purpose of this study was to obtain general geotechnical information regarding the subsurface conditions. You can also find a boring plan in the geotechnical lab reports. So the boring plan provides the location of different borings. For example, the boring plan of this project shows 12 core borings. And then if you check the appendix, you can also find the boring logs. So 12 boring location, there should be 12 boring logs. It has this, the Geotech Lab report is for Reich College of Education on campus. So they selected the locations, a total of 12 boring locations. They have the date of test, type of drilling. They used a hollow auger, information for the drilling rig, water level, logged by, hammer type, driller, and water level after 24 hours. There is also a notes section which says that the water level was not encountered after the termination of the boring, and caving happened at 24.8 feet. Then here you see the information. So this is the depth from the surface. It goes deep. There is a graphic log, and then there is the material description. The first 3 inches were asphalt plus 6 inches of ABC stone. Then we have different types of material, and the type of material is described: medium, dense, brown, tan, silty, fine to coarse sand. And then here on the right side, you can actually see the SPT results, a standard penetration test data. N value is provided here, and here you see blows per foot. Then from SPT, samples were taken for laboratory testing. So this was the first test that we covered in class, sieve analysis. 3 samples were taken for laboratory testing, and what you see here is the particle size distribution report, which is basically the results from hydrometer testing. We have 8 inches, 3 inches, which is 76.2. That's the upper limit for gravel. We have 1.5 inch, 3/4, 3 3/8 inch, and sieve number 4 here. It's the lower limit for gravel and upper limit for sand, and the sieve number 200 here. So we went over a part of the compaction evaluation. What you see here is the compaction test report. So for your class, we went over the part where you performed the standard Proctor test, and then you made these compaction curves. So for the 3 samples that they have taken, they also did the compaction test, where you see dry density or dry unit weight in pound per cubic feet versus water content. Also, so these are the sample IDs from boring location 5, 7, and 9. They took samples for further laboratory testing. It also specifies what was the depth of the sample, natural moisture content. Then from the sieve analysis, they also calculated the percentage of gravel, which is very low, sand 59, 41, and 33%, and fines 39, 58, and 64%. They also calculated the maximum dry density and the optimum moisture content. And finally, using USCS, they determined the symbol. So here we have sandy soil with silt, and these two are silt with low plasticity. Also, you can see the SPT results. With depth, we have the corresponding N value or SPT resistance. So more information, plan section AA for boring locations and boring B3, B5, and B10. Again, you can see different types of results. And then there usually is some type of recommendation. Foundation conditions based on the results of the soil investigation. The proposed first floor slab on grade area can be adequately supported on shallow foundations. So that is the recommendation, bearing on the residual soils. Partially weathered rock or newly compacted fill anticipated to be present at the bottom of foundation elevation. The total differential settlement potentials for the first floor area and the basement area should be less than 1 inch and 1/2 inch respectively. These settlement estimates are based on an allowable net bearing capacity of 3000 psf and 6000 psf